All right, it is 11 o'clock, so we're going to go ahead and get started. Thank you, everybody, for joining us today. My name is Sean Maurer. I'm the Technical Director here at the Smart Energy Design Assistance Center. Today, we're going to be talking about PFAS abatement for potable water plants. Um, if you have questions as we go through the presentation today, please enter those into the Q&A window. You can find that by hovering over the menu bar on your screen. Find that Q&A window. Enter your questions there as we go through and make sure we don't lose them in the chat. It's a little bit easier for us to keep track of whether we answered your questions or not. I do have Cassie on the line. She'll be monitoring both chat and the Q&A, so we'll try to capture all your questions as we move through. A little bit about CDAC and who we are here. We are the Smart Energy Design Assistance Center. Our mission is to help reduce the energy footprint of Illinois and beyond. We are an applied research program at the University of Illinois based in Urbana-Champaign. One of our major programs is the Public Water Infrastructure Program. We've partnered with the EPA Energy Office to provide no-cost energy assessments and technical assistance for potable water and wastewater treatment facilities to help reduce the cost of treating water. As part of the program, we provide a comprehensive report listing potential savings, estimated economics, funding opportunities, and ways to help improve your process, reduce energy consumption. We also look at trying to improve the process and impacting some non-energy benefits as well. We try to document all those in those reports. Another aspect of our program is continuing education, such as today's webinar. So this is the first in our series. The next few that we'll be having throughout this fall period and into winter, we'll be covering wastewater topics such as advanced aeration control technologies and some of the common energy efficiency things that we find when we go out and do assessments. So please do tune in to those future webinars. If you are interested in an assessment, please do check out our website, www.smartenergy.illinois.edu/water. We also host all our webinar content there. So if you want to find upcoming webinars and register for them, you can find that there. All of our past webinars are also hosted there if you're looking for other information. Why might you want to complete an energy assessment? If you're in an older system or you've never had an assessment before, you can help identify what opportunities your facility has. You can help plan for capital improvements in the future, uncover possible solutions for your facility. We can also provide third-party support for ideas that you already have for facility improvements. We've worked with a number of operators to incorporate energy efficiency improvements or controls improvements, things like that, into our reports so that they have some third-party support they can take to building councils or budget offices within their community to help fund and move forward with those projects. A big assistance there is also that we link to funding sources so people have access to those. What if you have a new system or you've recently upgraded your plant? So you've got new technologies in place, you've put VFDs on all your pumps and things. Well, there's always more ways to improve. We can always find some things that got left on the table, got budgeted out of the project. So we can help plan for implementing those as future opportunities. And there's always new technologies that we're researching and finding. The industry is always advancing. And so we can help bring those to the forefront so that you have an idea of what's possible with future developments. To apply for an energy assessment, we have a simple two-step application process. The first one is just a pre-qualification application on our website. It lets us know that you're in Illinois so that we can provide a no-cost assessment for you. Just indicates that you're willing to share facility information for us, or with us and our partners at ISTC as we do assessments to help provide the most accurate information back to you that we can. You have to allow us to come out and visit the site. And we do share those reports with the Energy Office. It is a non-regulatory entity, so we're not going to come out and find issues and report those. It's just for tracking of the effectiveness of our program with the Energy Office. Step 2 is data collection. We need to know what energy you're using at your plant. We need to know what flows are coming through it. So we gather that information from you. We'll hop on a phone call, go over some basic information about your plant to help us prepare for the site visit, know what we're getting into when we get on site. Also, we'll take that utility information and flow data to do some benchmarking for you, let you know where you stand relative to all the other facilities that we've assessed throughout the state. Once we've completed all that information, then we'll schedule the site visit with you. The site visit is usually about a 2 hour to 3 hour assessment, depending on the size and complexity of your facility. We'll walk through, document the different process components, the condition of equipment, um, mainly gathering name tag information off motor nameplates, things like that, to help us with documenting energy consumption, breaking out that energy into buckets of use, such as aeration, treatment, filtration, things like that. So that helps us target where to do energy efficiency improvements. For today's webinar, though, we're going to be talking specifically about PFAS abatement technologies. So by the end of this, you should be able to identify what the different available technologies are, compare and contrast them against each other, help identify which best applies to your site, and compare the relative energy use, waste products, capital costs, things like that associated with different PFAS abatement technologies. Joining me today is Neil McDonald from Aqueous Vets. He's got over 35 years of experience in the activated carbon industry, including escalating positions of technical and managerial responsibility. Most recently, Mr. McDonald served as the global sales director for PureGen Activated Carbons. He's the chair of the American Waterworks Association Activated Carbon Committee, a voting member of the ASTM D28 Activated Carbon Committee, as well as several other industry-related groups and committees. Neil has spent many years of his career in R&D and has published multiple papers, holds 2 patents related to activated carbon. Mr. McDonald also holds a BS, Bachelor of Science in Chemistry from the University of Pittsburgh, a Master's of Science in Chemical Engineering, and a Master's of Science in Colloids, Polymers, and Surfaces, both from Carnegie Mellon University. So Neil, thank you for joining me today and helping to present this material.
Thank you for having me.
So real quick, I'm going to provide just a quick overview of some of the most recent PFAS regulation updates, where PFAS are prevalent from studies that have been conducted in the state of Illinois, and just a high-level overview of different PFAS technologies, both established and well-known technologies that Neil will be getting into in a little bit more detail, and some of the emerging technologies that are out there for both treatment and complete removal and destruction of PFAS. And then Neil will get into design considerations for those technologies, operational considerations. I believe he's got a couple of case studies for people that have implemented PFAS treatment technologies near Illinois. So we'll help get you an idea of what to expect if you're needing to install PFAS removal. So why address PFAS? It's an emerging contaminant of concern. These are carcinogenic chemicals that are long lasting in the environment. They're very hard to destroy through natural means. So as a result of recent sampling and testing, the EPA has finally published maximum contaminant levels for certain PFAS that are prevalent. PFOAs at 4 parts per trillion, PFOS at 4 parts per trillion. The PFHXs, the hydrogen sulfide compounds, 10 parts per trillion, the Gen X chemicals at 10 parts per trillion. And then there's mixtures of these that have a hazard index of 1 or less as the maximum contaminant level. So the hazard index looks at a couple of other PFAS materials, has some concentrations. You can see how the hazard index is calculated there at the bottom. All the contaminant concentrations are to be reported in nanograms per liter or parts per trillion. They're an equivalent metric there. So June 25th is when this regulation became effective as a national primary drinking water regulation. That triggers a 3-year cycle to complete initial monitoring and sampling for PFAS at public water facilities. So if you haven't started sampling yet, it's a good idea to get on that early and give you time to start planning for addressing PFAS if you do happen to find it. After that 3-year period, public notice is then required if PFAS is detected to let the community know that PFAS has been detected and you're working on implementing technologies to abate that in the water supply. And that notice is just contained in the annual water quality report along with other notices to the public. 5 years out, so 2029 is when the target date for actually implementing treatment technologies. And if you don't have the ability to remove PFAS at that point, that's when you start having to do public notice of violations of the water quality standards. So though There's usually a 3-year adoption timeline for the drinking water regulations, but EPA has used a variance in the Clean Water Act to allow a 5-year implementation due to the need for capital improvements, planning, design, construction. There's a lot of implementation considerations for PFAS technologies, adding additional filtration, infrastructure, piping, things like that. So they have extended that 3-year adoption timeline to 5 years out to 2029. So who needs a test for PFAS? Everyone should be testing for PFAS, but you're at the highest risk if you're near a site where PFAS-based aqueous firefighting foams were used, such as firefighter training sites, airports, military bases, where those foams may have been able to wash out into ground and leach into the groundwater or run off into surface water areas. Um, if you're near manufacturers of PFAS chemicals or materials that use PFAS, those manufacturing sites may have leaked PFAS materials, may have been dumped out. As part of the manufacturing process, dusts, things like that may have been contaminated with PFAS that then get carried out of exhaust systems. Multiple different ways that PFAS can enter into the environment from manufacturing. So if you're near those sites, probably a good idea to test for PFAS. And then municipal treatment from landfill leachate, industrial wastewaters, other potentially PFAS contaminated water upstream of your public water supply. You're going to want to be checking to see if unregulated PFAS discharges somehow got into your supply water, to see if you need to implement technologies to treat it. So the image on the screen here is an EPA sampling completed as of 2021. They've tested at over 14,000 communities. 68 of those were found to have concentrations above the health-based guidance limits. 81 concentrations were below those limits. So PFAS was detected, but they're below the health-based guidelines. So treatment may not be necessary. And then 15 had unconfirmed detections where an initial sample detected PFAS, but follow-up samples did not. So particularly those communities that had concentrations that were below the guidance limits, might be a good idea to increase sampling frequency, test those again, make sure you don't have any spikes that come through. But for the most part, 88.5% of sites you can see on this map, all the blue dots were undetectable PFAS levels. So they're either below the detectability limit or just not present. So for the most part, PFAS seems to be in the northeast corner of the state, down around St. Louis, and then some manufacturing and military base areas scattered around the rest of the state. This presentation will be available, and there is a link underneath that photo to that GIS map if you want to access that. That will be available on our website as part of this presentation. So how do we address PFAS? This is the content that Neil's going to be getting into in a bit more detail. But ion exchange resins are one methodology. Certain resins are better adapted to certain PFAS than others. You can use mixes of resins to fully treat PFAS. So you can optimize your removal. Granular activated carbon is probably the most prevalent treatment methodology for PFAS removal. It's really great for removing long chain PFAS like the PFOAs and PFAS. But the short chain stuff, you need a longer contact time or a larger containment vessel, so that the water is in contact with that activated carbon longer to remove shorter chain PFAS. It's a little bit more difficult. Reverse osmosis is another methodology. It's good at removing all PFAS types. You do have to have some pre-treatment to prevent scaling, things like that, for the RO system. But it's similar to the other systems where you're going to want to remove large solids, contaminants, things like that, so that your ion exchange resin or your granular activated carbon or reverse osmosis is only removing the targeted things that you want it to remove. So this chart, I'm going to kind of overview it quickly here. Just a relative scaling based on reviewing multiple papers on the different treatment technologies. Relative footprint, ion exchange is somewhere in the middle. Activated carbon is generally the largest, especially if you're treating for those short chain PFAS compounds. Reverse osmosis has the smallest footprint. Unfortunately, it also has the highest capital costs and operating costs. Activated carbon tends to be somewhere in the middle as far as capital cost, mainly because of the larger tanks to hold that filter media. Ion exchange has probably the lower capital costs, smaller tanks, smaller footprint. The operating costs are a little bit higher for ion exchange as those resin materials are a little bit more expensive than the activated carbon materials. Energy consumption, activated carbon and ion exchange are very similar to each other. Again, activated carbon can be a little bit higher just due to the larger tankage. Reverse osmosis is by far the highest for energy consumption. Waste streams that come out of these for ion exchange, you get a backwash brine when you're recharging ion exchange, similar to what you're doing now with softening plants. With activated carbon, you've got backwash water, kind of like you would get with a sand filter. For reverse osmosis, you get a concentrated brine that comes out. So a liquid stream, but it's highly concentrated with salts and PFAS compounds. Media replacement intervals, activated carbon's probably got the shortest. Needs to be replaced more frequently. Ion exchange is somewhere in the middle. Reverse osmosis has a longer replacement interval for those membranes. And then waste handling. For ion exchange, you can landfill that media or send it to an incineration plant are the most common ways to remove that concentrated PFAS that builds up in that resin. Activated carbon, you can send that contaminated material to a thermal reactivation plant, reactivate it, and then reuse that activated carbon material, or it could be landfilled or just incinerated. For membranes, those just get discharged to a landfill. We do want to note details on that media replacement interval does have a lot of influence based on the source water and what other contaminants may be present. Some contaminants can interfere with PFAS removal because they have similar interactions with these materials, and so may impact both backwash, replacement intervals, things like that. Some of the emerging technologies for public water systems. There are multiple technologies available that simultaneously concentrate and then destroy PFAS. Most of these technologies are at bench scale or pilot scale testing phase. There are some that are commercially available but handle limited flow rates. We'll talk about those on the next slide here. But there are very few that are commercially available that actually destroy PFAS in place as part of the treatment process. Because it's more economical to destroy concentrated PFAS, it may be more economical to deploy these kind of technologies at the wastewater treatment plant rather than at the water treatment plant, especially since wastewater from the water treatment gets discharged to the wastewater plant anyway. But if PFAS buildup in sludge that's being land applied might be a concern, then maybe there's an agreement with your local wastewater plant that the on-site destruction of PFAS at the water treatment plant might make more sense. So as I was saying, lower PFAS concentrations from backwash and ion exchange and granular activated carbon is not ideal for these destruction technologies. There's a lot more water than the PFAS in there, so you need to concentrate it again before sending it through a destruction process in order to limit your energy consumption needs. RO concentrate is already highly concentrated, so it's a little bit better candidate for sending straight to a destruction technology process. Again, incineration is probably the most common step right now for destruction of PFAS. Although research is ongoing about whether PFAS is fully destroyed or whether long chain is broken down into shorter chain PFAS materials. I was actually just reading a research paper this morning where they were finding some shorter chain PFAS in the ash and things from incineration. So there may need to be additional treatment steps from incineration that we're not aware of. But usually incineration is done at a central waste handling site. It's not done on site at the treatment plant. So you'll ship your activated carbon off or your resin off to another plant where that incineration is done at a hazardous waste handling facility. But there are those concerns. So other technologies may be slowly replacing incineration if it can't address these issues where PFAS can continue to get into the environment after that treatment process. So some of the technologies that are available, electrochemical oxidation is essentially um, two electrodes in the water. You've got a cathode and an anode in the water. You set up um, an electrical field between them. PFAS is attracted to the anode, um, and because of free radical reactions, water itself breaks down into hydroxide and hydrogen ions. Those can interact with the PFAS and start breaking up that long chain. Um, Direct electron energy off of the anode itself can also destroy the PFAS. Primarily, these are bench scale tests, but have pretty good results for PFAS removal, 70 to over 90% removal. Um, some additional research on how to upscale the systems, make them cost effective, um, concentrating the PFAS to get more energy efficient process, avoiding toxic byproducts. PFAS contain chloride ions, they contain sulfides. These things can recombine with some of the other things and create some pretty nasty acids, hazardous gas fumes, things like that. So tuning the process where those don't occur or are rapidly degraded themselves before they can be emitted to the environment is part of the ongoing research. Plasma destruction using high temperature and UV light. Um, Plasma itself creates shock waves that can break apart long chain polymers. And then electron excitation. So your high temperature, high energy environment, electrons shoot out of different molecules. Those can break up PFAS. So far, there's been some small scale pilot testing, very, very high removal rates, close to 100%. But again, you've got co-contaminants that can impact the process. And then as PFAS break down, they can recombine with those co-contaminants and create hazardous chemicals. Optimizing the process conditions to minimize energy consumption is also part of the ongoing research. Photocatalysis is another option. So using light and an oxidative material to excite electrons to break up the PFAS works very similar to the plasma option. So far, this has only been tested in the lab on optimized, lab-based materials. It hasn't been used on real-world samples of PFAS contaminated waters. So they don't necessarily know what interactions are going to be with other co-contaminants. Sonolysis is using shockwave degradation with ultrasonic frequencies. So again, this interacts with molecules in the water, creates free electrons, free radicals, oxidative compounds that can break PFAS apart. There have been some labs, bench scale testing using, again, lab created PFAS concentrated water. So it's doesn't have co-contaminants in it, but has had pretty significant removal efficiency. Again, things that they're working on for that research is upscaling real world testing on actual contaminated water samples, optimizing frequencies to reduce reactor size and promote energy efficiency. One that is currently available on the market now is supercritical water oxidation. So they use high pressure, high temperature, get that water into a supercritical state where things are then perfectly dissolvable into water. Because of the high energies involved in this, it breaks PFAS apart. Small scale systems are available, I think up to 50,000 gallons per day. Or yeah, I think that's the size that's available. There's two companies I'm aware of that provide supercritical water oxidation. Comes in essentially a 40-foot cargo container, pre-built to do energy recovery and things like that. So once you start the system up, it can be self-sustaining. You get better than 99% removal of PFAS. And your byproducts are essentially non-hazardous gases like carbon dioxide, nitrogen, and then mineral salts. The chlorides recombine to create chlorine salts, table salt, things like that. These do have an impact on pH, so that's part of the research is optimizing the process, either through using additives to control pH, and how to address abrasives, things like that come out in the process, so that it can be maintained long term and isn't degrading just through its own process of creating these salts other co-contaminants that move through the system with PFAS um, that can degrade the internal materials. And then we've already talked a bit about incineration. Um, it's available, can treat large scale volumes of contaminated materials such as the ion exchange resin and activated carbon. But again, the main concern here is that we're not fully certain of what happens to all of the PFAS in this treatment because we can't sample for everything right now in air samples and waste samples of the ash product that comes out of incineration. They're still working on how to actually detect, capture samples of these things, and then see what's fully happening in that treatment process. So those are those available technologies. I'll now turn it over to Neil to talk about the established technologies, to let you know what's available there.
All right, perfect.
And you should be able to share slides there, Neil.
Okay. It says host disabled participant screen sharing.
Oh, let me fix that.
Should be fixed now, Neil.
Okay. Can you see that?
There we go.
All right. Yeah, we're going to focus on the pressure vessels. So we have what we like to talk about as our 4 tenets of pressure vessel design. And this is not only for activated carbon and ion exchange. There's some other media coming out now. I guess the good and bad of PFAS. The bad part is obviously the health issues with it. The good part is a lot of academia is getting involved in these treatment technologies, and there are some new products coming out. So briefly go over a little bit of those. Where's my screen moving? There we go. So we'll talk about some of the factors design that contribute to the OpEx. This is actually one of our systems here that was installed in New Jersey, and as I mentioned, this is not a carbon or ion exchange. It's a product called Fluorosorb, which is a modified clay-based material. So this is at one of the sites in New Jersey. We mentioned the 5-year time frame in terms of having to do something here. 5 years may seem like a long time, but it's really not. You got a couple of years of sampling. You got site surveys. A lot of places don't have anything at these sites. Then design and construction, so it can take a long time. What we like to do is look at this again for the overall the overall life cycle cost of the system. Everyone focuses on the price on bid day, which is fine, and that's generally and unfortunately how decisions are made in terms of what's put out there. What we got to think about is these things are going to be out there for 25 to 50 years. As Sean mentioned, the media is going to be changed out. You have to look at other things that affect the overall cost during that time frame. So what do we look at in terms of the mechanical designs? There's a variety of different systems out there. They all work. There's ways to look at saving costs. For instance, lower profile. The ion exchange resin, again, is typically going to be a smaller system, means reduced building cost. You have states, for instance, like California, that don't like tanks sticking up, so you have to put them in houses. You get up into the Northeast, where obviously we have, I'm in Pittsburgh, so we get up here in the winters, you can't have these outside, and they need to be inside and insulated or sometimes heat traced to keep the water flowing. The distribution system is extremely important, how the water is not only brought into the vessel, but how it's taken back out. That'll optimize the media usage. We'll talk about PFAS in general here in a little bit in terms of the media usage. As I like to say, PFAS is different. It acts different than your typical compounds that we run into with the various media. Head loss is obviously something you need to take into account. So obviously more pressure drop is going to be related to energy. And then just your long-term operational maintenance costs. This is just a quick little table that you can, again, people don't take into account, again, on the price of bid day. So some cases, these things have to be in a building. The system I just showed you there, the one in New Jersey, is actually inside. So that was an existing building. The challenge there was getting the vessel in the building itself. If we went with activated carbon or something like or even the ion exchange media, that vessel probably would not have fit in the building. We actually managed to roll that one in on pallet jacks to get it in the building. So we got to look at that. We got to look at pump sizes, insulation, how long your electrical runs are. We have the luxury in places like California where we had larger areas where we didn't have to worry about things like that. We start getting into the Northeast, and some of these are existing facilities that don't have a lot of room. So we just have to take all that into account. And again, your pumping costs, annual heating and cooling costs, these are all things that go into the long-term operation. So we talk about 4 tenets of pressure vessel design, and the 4 tenets are corrosion management, hydraulic engineering, media optimization, and long-term operability and maintenance. So we'll go into each one of these in a little more detail, but these are the 4 things that you need to take into account when you're thinking up a system out in the field, and again, for 25 to 50 years. Other things to consider, again, it depends on the site. You got to look at, the site flow. What are you trying to remove? Again, activated carbon in particular tries to remove anything organic. So, we're getting into situations now where people are looking at surface waters. Most of the work to date has been done on groundwater, but it's starting to show up in some of the surface waters. You got a couple PPT of PFAS compounds, but you got a couple ppm of other organic compounds, and that's going to affect performance over time. The operational considerations, we always take into account the hydraulic loading rate, the empty bed contact time. When it comes to activated carbon, that empty bed contact time has more or less been dictated by the EPA at 10 minutes. Because of the nature of the PFAS compound, all these systems are 2 beds in series. So you got 20 minutes of contact time. So depending on your flow rate, these systems can get rather large. The activated carbon, the fluorosorb media, things like that need to be backwashed when you first put it online, and may have to periodically if you start seeing some increase in pressure drop due to solids buildup or inorganics in the water. Obviously, the operation pressure, you need to consider the site limitations. Again, some of these sites are relatively tight quarters now. You got 10-minute contact time for activated carbon. The ion exchange resin and the specialty medias are down around 2 to 3 minutes. So these systems will be much smaller with these other media compared to the activated carbon. You also need to be able to access the media. Again, they're going to be changed out periodically. The activated carbon, you're probably looking at 6 months to a year in some cases. The ion exchange resin is a little bit longer than a year to a year and a half, maybe even up to 2 years, depending on concentration. You have to be able to get that media out of the system, get the new media in, and obviously be able to service the vessels themselves. So we'll talk about the design of the system. So the first step here is the history of the underdrain. Started back in the 80s with the head and lateral design. Then it moved to what's known as the external cone. After that, it moved to an internal cone. So that cone you see on the bottom picture there is now inside the vessel. And then we moved to the external ring header and the external ring header low pro, which is a lower profile system. Again, trying to reduce the height of these just to make them a little more visually appealing, so that people don't look at it as a big tank farm as they drive by. All of these systems work. They will all meet your treatment needs for PFAS. There are pluses and minuses to them that we'll go over here a little more in detail. So these are the internal designs. So you can see in the header and lateral, there's basically a main pipe that comes through the middle with laterals coming off it. The external cone has a distribution system on the bottom, which is 6 or 8 nozzles, depending on the size of the system. The internal cone is a design that has 1 nozzle per every square foot of surface area. And then the external ring header, where the system, if you look down on the bottom of that design, you'll see that the distribution system is on the outside. The collection system, there's nozzles that come up into the vessel. So this system can be easily, the maintenance on it's a little bit lower, trying to, if there's any repairs needed down the road. So what's important about selecting the design? You got to evaluate the design to look at for the cost saving standpoint, and then evaluate the different media. It's not as simple as just using the same design for each media. There's distribution systems that need to be taken into account. There's, you can look at these designs in terms of energy savings, maintenance costs, and optimized media usage. I've been in the industry now for 35 years. I can tell you when I first started on the activated carbon side, the systems were just made big enough. The upper distribution systems weren't really looked at. They used the upper part of the carbon bed as their flow distributor. With the PFAS application in particular, we found we can't do that. So there's been a lot of CFD modeling done now to optimize these designs to make sure the performance is better. And again, these are things that can be put into the design specification to benefit the end user. Something no one wants to think about, but you need to, is corrosion. Obviously, these vessels again are going to be out in some cases outdoor locations. Obviously, there's water flowing through them. Some of these waters can be a bit corrosive. Some of the most corrosive waters that we're seeing are some of the cleanest ones. Some of the groundwaters don't have a lot of mineral in them. Just a little bit of PFAS from a spill or something. Those things can have a tendency to be pretty corrosive. So it's something you need to think about. So when you design the system, you got to think of the process parameters: the temperature, velocity, pressure, water chemistry, construction parameters, weldings and coatings. All these vessels are lined with a coating, and that's per the specification. The geometry of the drainage, you don't want any place where there can be something trapped. Dissimilar metals, obviously try to avoid dissimilar metals. Crevices, again, try to minimize those. Those are places where corrosion could start forming. And over time, you are going to have some. You're just going to have to compensate for it. So again, we're trying to reduce this. And in inspections, obviously when you're doing a media change out, it's the optimal time to be doing an inspection of the system itself. These are just the galvanic series. Obviously, we try to keep the dissimilar metals apart from each other. There's actually a NACE standard on all these in terms of material selection, electrical isolation, barrier coatings, that type of thing. On the right here are two pictures of that's the head and lateral design, the top one, and the bottom one here is the internal cone. You can see the corrosion that has formed, and obviously, if that's the case, someone's going to have to go in and repair that. The one on the bottom here, the internal cone, looks to be some over tightened fittings that cause corrosion where the joint is. The coating is extremely important. And again, there are NACE standards out there. You try to avoid sharp edges. If you look at the picture on the right there, this is a case where there was a sharp edge. And what will happen is the coatings will start to shrink and pull from the sharp edge, and that can leave a crack that exposes the vessel itself. So again, a place where corrosion could form. There's third-party testing that can be done. It's actually called a holiday test. It's an ASTM standard D5162. So again, this is something that a third party can do. And it's highly recommended to make sure that you aren't having any potential corrosion issues. Ideally, you'd like to have a homogeneous lining. In some of the system designs, that's a little more difficult to do. So again, these are just things that go on with the different system designs that you need to take into account. One thing you try to minimize is vessel entry. Obviously, if someone has to go inside the vessel, that means they could potentially be standing on the liner. So that's another potential for corrosion down the road. So again, these things can be engineered around. Most important part before the lining's put in is making sure that the internal of the vessel is properly cleaned. So you can go from basically just from the initial internals having some rust and things like that on them. As you go to the cleaning, you can get to the near white. To go from near white to white metal is about another 10 minutes, 10 to 15 minutes. And we'll just ensure that it's a better coating once it's put in the inside of the vessel. So these are just again, it's not it doesn't seem like a long time to go that extra little 15 minutes to get to a white metal. Hydraulic performance, and every system is designed around a couple parameters here. What we're trying to do here is, again, optimize distribution of the flow. This is actually a CFD model on the right-hand side. Again, years back, no one really cared about what happened in the top third of the vessel because the activated carbon in particular, the bed depth was deep enough that you didn't have to worry about it. Your top foot of the carbon was your flow distributor. Now it's extremely important for a couple reasons. One, again, from an activated carbon standpoint, the material, the mass transfer zone, where absorption takes place, is very long for PFAS. So we can't be wasting a foot of carbon bed as a distributor. When you get into the ion exchange resins, these are round beads. They're all the same size and shape. If you have flow going in one particular place, it will actually push the beads up to the side. We've actually do have pictures, not in this presentation, but we do have pictures of the inside of a vessel where all the beads are pushed up to the side of the vessel. So that's extremely important. And in the under drain, so it's obviously we want plug flow going down through the bed. We want nice even flow, and then we don't want it to go to like a single collection point. We want to make sure that the water as it comes down through the bed is also collected uniformly. This optimizes the pressure drop as well. Again, there's a pumping cost that we need to take into account, so we try to reduce the pressure drop as much as possible. So there's basically different the different designs can give different pressure drop through the system. So again, something to think about. Bed expansion is going to lead to the size of the vessel as well. So for an activated carbon system, you need to expand the bed 30% when you first put it online. When you do that, you're backwashing some carbon fines out of the system, and you're also stratifying the bed. Stratifying the bed means the little particles go to the top, the big particles go to the bottom. That also reduces pressure drop in the long run. But obviously, you have to have a section of the vessel where you can expand the bed into, so it will increase the height of the vessel. Mentioned CFD modeling. Again, there's software out there that most people are using now. It's becoming more and more prevalent, again, because of the system design. Obviously, we're trying to make these things as small as we can and still get the nice distribution. So it provides a model of the internal velocity and pressure distributions in the system. It can be used to validate design choices. So again, that upper distributor in particular, there's been a lot of design changes on that just to make sure that we're getting nice plug flow. Ideally, we like plug flow from the distributor the whole way down through the bed without using the bed as a distributor. What that does is it allows a nice uniform mass transfer zone that moves down through the bed, again, where the absorption or the ion exchange is taking place. And then the under drain allows for a collection of the water, again, without increasing pressure drop too much. So this is just a visual, as you can see. So what we're trying to do is get a nice even flow down through the actual media. The media optimization, and this is my primary job within the company, is looking at the different media. The one thing I'll say about PFAS is there is no silver bullet. We have applications where we're using activated carbon, some with ion exchange, some with the Fluorosorb media. We do a lot of work on the water chemistry up front to make sure that we get the best media. Within our company here, we're not producing any of the media. We have partners that do that. So we have the ability to select the best media. So for instance, as you go out to California, you see a lot of ion exchange. You get up in the Northeast, you start seeing a lot more activated carbon. So optimizing this media is extremely important. The bed life on the activated carbon systems compared to other organic compounds is significantly less. So we got to do the best we can to try to optimize the performance of the media. Again, we want to make sure we get a nice plug flow down through there. We're going to optimize the mass transfer zone. So the mass transfer zone, again, is where the absorption is taking place. The top of the mass transfer zone is basically the influent concentration. The bottom of the mass transfer zone is basically the initial breakthrough with a detection limit. So it's extremely important in this PFAS application in particular with the 4 PPT limits. That's basically the detection limit of the analytical labs. There's no early warning system in PFAS. You start looking at compounds like TCE, PCE. We can sample the vessel, and we know that when we start seeing some breakthrough, we got a period of time before we're going to have to change the media out. When it comes to PFAS, because we're 4 PPT, most of the labs are just reporting around 4 PPT. You're going to be going 0, 0, 0, and then all of a sudden you're going to be at 4. And that's why we have two vessels in series. That's why we need to optimize the flow down through the system so that we do get better performance. Something to think about when you look at these vessels. If you look at a lot of the bid specifications, especially when it comes to the activated carbon, they'll say 20,000 pound vessels, 20,000 pounds of carbon. Again, I started in the industry in 1989. That 20,000 pounds came from the density of the product back in the 80s and 90s. The densities of these products are all over the place now. You can have products as a density as low as 22, 23 pounds per cubic foot, up to 33 to 35 pounds per cubic foot. And obviously, we do everything based on contact time. So in a 10-minute contact time, you have to think about the volume of media you have in there. When we put the volume of media in there, no matter what it is, you're going to have some material that's going to sit underneath the drains on the bottom of the vessel. How much media is under there is extremely important because it's essentially unused media. It's media that is not going to be in contact with the water, or it's going to be just in contact with a short period of time. So the different designs can have a different amount of media sitting underneath that drain. So the external ring header is about 62 cubic foot. The internal cone is about 108, and the head and lateral can be upwards of 169. Again, this is media that's not being utilized. So if you want to look at it from a cost standpoint, you look at it from 25 years, it can get pretty significant. If you're looking at it from a carbon standpoint, it can be anywhere from 100,000 to 250,000, depending on design. If you start looking at it from an ion exchange standpoint, it could be $500,000 to $1 million of underutilized or unutilized material. So the long-term costs. Different designs, again, you have to take into account what this long-term cost is going to be. The external ring header design here, you have the ability to drop that system down on a pallet jack and be able to inspect the nozzle, so you don't have to enter the system. It allows for internal inspection from the outside of the vessel. So it has the under drain. It meets all the pressure vessel ratings of a vessel as well. Typically in the specifications, these will be designed up to 125 PSI. And that's something to think about because the vessel itself is rated to 125 PSI, but in some cases, for instance, the internal cone may not meet that 125 PSI rating. Maintenance, again, trying to reduce the amount of confined space entry for two things. Obviously, confined space entry is from a safety standpoint, and two, just having someone go in the vessel. You don't want to have to be walking around on the internal liner. Carbon versus ion exchange, things to think about. Carbon's pretty abrasive. You can find it in toothpaste now. It works great to whiten your teeth, but unfortunately, it's taken off a little bit of the enamel at times as well. The ion exchange resin, you don't necessarily have that problem because it's a round bead. The activated carbon requires backwashing, whereas the ion exchange resin does not. In fact, the resin manufacturers do not recommend backwashing an ion exchange system. So again, something you need to take into account. If, for instance, your water has high iron or manganese in it, because those are the type of things that need to be removed prior to the ion exchange resin system. So the change out, different ways to remove the media. So again, these are going to be changed out periodically. There are a couple of different ways to do it. Generally, the larger vessels, and these can be up to 14-foot diameter now, typically use a slurry method where there's basically a transfer line on the vessel that a truck comes out. Basically, there's an air compressor and the media is pushed out of the truck. That truck that you see there has basically two tanks in it, one emptied and one with the new media. The old media is pushed into the empty side, and the new media is installed after the vessel's rinsed out and disinfected. The smaller systems are typically done by a vacuum truck, and the loads are typically put in by bag loading. So basically, a 1,000-pound super sack of carbon will be lifted up over the vessel, and the media will be introduced that way. Every time you do a change out, you should also do an inspection of the internals of the system just to make sure there's no corrosion. There's a little bit of discussion on the reactivation process and incineration destruction technologies. So in theory, you can reactivate the activated carbon. And reactivation is basically sending it back through the same process that was used to make it. This is typically done in a rotary kiln for the drinking water carbons. Temperatures up to around 1,000 degrees C. the material is exposed to. So again, if you look at the physical properties of the PFAS compounds, in theory, they should break down. The gas coming off of the reactivation facility is run into an afterburner. So again, this is all so you're not discharging anything to the air. What we're trying to do is restore the material back to the virgin grade. So carbon is typically looked at by an iodine number. Most of the specifications out for PFAS are 1,000 iodine number carbons, typically bituminous coal-based materials or sub-bituminous coal. There's some coconut was used initially, and we found out that coconut does not work for PFAS at all. So all these are coal-based carbons. What we're trying to do again is get the iodine number back up. You're never going to get it back up to the 1,000 iodine. You're probably, in most cases, getting it back up to around an 800 or so. Again, there's been some work being done, or has been done to show that it potentially been reactivated. I'm aware of a couple places that are using potable water reactivated carbon from PFAS. They haven't, one hasn't been very successful because they've had some metals leaching coming off the reactivated carbon. For it to be reactivated, you have to get your own carbon back too. This is a requirement within AWWA that the 20,000 pounds you took out of your system gets reactivated. They add makeup carbon because you lose about 10% when you do the reactivation. And then that carbon is put back in that exact same system in order for it to be used as potable react. There is use of the material, it is being reactivated and used in wastewater applications in some cases, so it's not going back for potable. The advantage here is you get a certificate of destruction. So the end user will not have something that's going to be on their books for years. So basically these compounds are destroyed so that you won't have a waste issue 10 years down the road. The incineration process, this is typically for the ion exchange resins. And again, there are specific sites in the US, so not every incinerator is taking the ion exchange resins. They're dedicated sites for the PFAS application. And again, these are incinerated, and you will get a certificate of destruction from it. Other things to think about are what else is going to be on the system. These sites are, and again, a lot of cases are new sites. Or sites, that don't have a lot of places to put equipment. So typically what we like to do is make sure everything is hooked together at our facility before it leaves. But in some cases, people do have put expansion joints in just because of the unbalanced ground or, not flat where the system is. So an expansion joint can help out with that a little bit. We typically don't like to do that because, again, these are rubber. They can, they're exposed to sunlight and UV. They will degrade over time. So again, we try to avoid those. And again, it's just making sure the system's aligned when you put these out there is a better design rather than putting an expansion joint in. So just some other things to think about when you're putting the systems out there. So we'll get into two specific examples here of ones that we put out, and this is Stuart, Florida. Stuart, Florida, right now is using a two-system design with pre-filters. They are designed to run lead lag, but they are running, they're designed to run lead lag or parallel, but they're running lead lag. So we are running two beds in series. And then it's the external ring header design. So this system has been operating for several years. Down in Florida, they started testing several years ago and made the decision to just go ahead and treat the water with ion exchange resin, and it's actually the Dow PSR2 Plus is the resin that's being used here. So it's operating in 700 GPM. It can be up to 1400 GPM designed for the system. Again, the ion exchange resin is in there with a 3-minute contact time, and the overall system height is a little over almost 16 feet high. Just to give you an idea of the height of some of these. The next one is Yorba Linda, and this one is the largest PFAS plant in the world right now. So it is operating, this is in Southern California. There are basically two vessels in series. Again, the piping in the middle allows you to switch from the lead vessel to the lag vessel. So when we go do a change out, the media will be taken out of the lead vessel, The lag vessel will then be put into the lead, and fresh media will be put into where the lead was, and now it will be the lag vessel. So the piping and valving there allows you to switch the flow to accomplish this. And this is the site in Yorba Linda. It's actually at their headquarters. So the building here is their headquarters building. So they are treating all the water in one location. There are 22 vessels, 22 12-foot diameter vessels with ion exchange resin, treating the water here in Yorba Linda. So 6 pre-filters on this. They're bag filters to remove solids. Again, with ion exchange, you have to make sure the water coming in does not have any solids. Again, iron and manganese can be an issue because these things can't be, or should not be backwashed. Because the material's all uniform beads, if you backwash them, you're going to start mixing the materials, and you can have desorption. All of these media, carbon, ion exchange, the Fluorosorb media, there is no chemical bond formed with the PFAS resin, so you can definitely have some what's called desorption or sloughing occur if you were to mix up the media. So again, 22 vessels, 2-minute contact time. There's some surge tanks. There's all kinds of other things at the site chlorination facility. So it's a rather large system treating at the actual headquarters for Yorba Linda. If anybody went to the ACE conference in Southern California this past year, they actually gave a tour of this facility. So just to kind of summarize, again, a lot of things to take into account when you're designing one of these systems. Like I said, there should be a lot of upfront work in terms of water quality, in terms of optimizing not only the system design, but the media. And then the long-term operation needs to be taken into account. So this design has been vetted for over 25 years. It works very well. And again, it's trying to get away from the price of bid day and thinking about how long these things are going to be out there and what the overall cost is going to be. So I thank you for your time. I think we managed to get in and maybe have some time for some questions.
Yeah. We did have a couple of questions come into chat that I noted. First one is this type of project a good fit for energy savings performance contracting? Depends.
That's, I
Um, so a brand new installation, you're probably not going to be doing an energy savings performance contract for a brand new installation. You're going to be designing upfront for efficiency as well as the other considerations for your site. But if there's an existing site that you're using and maybe you're adding on PFAS to an existing site, you might do performance contracting on that existing site to optimize energy there, so that your overall increase in operating costs in terms of energy is minimized as much as possible. I don't know, Neil, if you've run across that at some other.
No, it's, this, as I said, this application is different. You got a lot of places where, particularly in the Northeast, that have been using carbon for years for other compounds, and now they're looking at what they need to do for PFAS. So yeah, there may be places where they need to add on, an additional system. So obviously that's going to be, energy costs or something they're going to have to take a look at.
And then we had another question about what usually happens with RO brine that has removed PFAS. So right now, the regulations are on the potable water side. So RO brine typically gets discharged to the wastewater system and goes to the wastewater plant. There may be future discharge permitting requirements in the works, but right now that concentrated PFAS just goes to the wastewater plant, and there may be a community agreement to do some treatment for PFAS removal there, so you're not discharging back into your waterways. But there's not currently regulation on that. Don't see that any other questions have come into the chat here. Neil, I did want to touch base on your experience with activated carbon. You mentioned a little bit about the coconut wasn't as
Yeah.
good with PFAS removal. Are there other types of considerations for other types of activated carbon?
Yeah, what we found with the coconut, if you the history of coconut is basically it's generally used in applications with low concentrations in clean waters. So, for instance, your home water filter, your Brita pitchers, things like that are coconut shell carbon. So when PFAS first came out, the concentrations we were looking at, at PPT, were like, what's perfect for coconut? What we found is the kinetics are so slow, mainly because these compounds are obviously, long chains. They have some chemistry to them that's a little different than, for instance, your chlorinated solvents. So the first coconut system was put up in, I think it was Massachusetts, and it didn't work well at all. So now the specifications are around the coal-based carbons. A lot of these coal-based carbons are ones that have been around for years. There is some work being done right now to develop some new products in targeting the PFAS application. So again, it has brought out some new research, which is a good thing. But yeah, everything in these bid specs is pretty much written out as a bituminous or sub-bituminous coal-based carbon.
Okay. Question about the PFAS map that we had put up. The blue sites on the map were ones where PFAS was not detected. So it might not be zero, but it's below the detectability limits of the sampling procedures. Um, so, uh, in effect, as far as permitting and regulatory requirements, yes, those were zero sites. Um, the 2029 deadline is the date that you would start issuing notifications to residents of PFAS. If you're not treating for it, that and it's in the water, you would have to notify if it's above that those minimum concentration limits. Then yes, or sorry, maximum concentration limits. Then you would have to notify residents that the contaminants are in the water and that it needs to be corrected. I don't see any other questions that have come in. Thank you, everybody, for joining us today. Neil, thank you for your insights. Appreciate
Thank you
it.
for having me.